All right. Here we go. Where's my calculator? Yeah. So we're going to start with number 6. And then go on to 11. Alright. I think I'll make that a little bit bigger. Yeah, that's better. Alright. So, a meter stick passing a spaceship has a length of this, so it's the speed of the spaceship. Express your answer in terms of the speed of light, c. So, this is number 6. Alright, we should probably start with the very basics. Speed of light is what? Is constant in what? In all frames of reference. Right. That's our basis here. What happens to length as you move? So that would be my next fact. Length contracts or gets shorter when objects move. Let's see. So I've kind of got my main concept, I've got my fact, but I need something that ties it to this one. Let's say like the meter stick is shorter while moving. And you could put that groundbreaking one of how long is the meter stick when not moving?
1 meter.
Yeah. Some people may not realize that. So you might want to put that, the meter stick is 1 meter when not moving. Just to help out, the people who need it. Alright, so then we would go to our handy-dandy equation sheet and look down at the special relativity part because we're looking between frames of reference. And we're dealing with length. So do you think we should use the time equation, the length equation, the momentum equation, or the inertia equation? The length equation, probably. L equals L naught over gamma. So, we have L equals, stack that a little bit better. L naught over gamma. And we remember our factoid that gamma is always greater than 1, right? So which one is bigger, L or L naught?
Oh. Yeah. No, L naught. I decided that. L naught.
L naught. L naught is always greater than L. I just wanted to see how many times I could get you to flip back and forth by just not.
You got me the most time.
I think so.
That's not right.
That's not right. So that means that L naught is in the stationary, let's call that the Earth frame of reference, and L is in the ship's frame of reference. Okay? And of course, we probably should have written down gamma. I prefer to write gamma this way. 1 over the square root of 1 minus parentheses V over C quantity squared. Because, like, if I'm told that the velocity is 0.85 c, well, v over c is 0.85, right? And also, if I'm, like in this one, they want to know how fast the ship is going. If I solve for v over c, that's really easy to put into terms of c, right? I want to avoid writing the number 2.79, blah, 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 as many times as I can. So that's what one of my goals is going to be. So this really, let's see, they want to know v over c, I think, right? They want to know how fast, expressed in terms of c. So really, we're finding v over c. That's going to be our relationship in here. So we said that L is the smaller one. So L is that 0.96 equals L naught, 1.00 meters, over 1 over the square root of 1 minus v over c squared. And just solve for v over c. That'll give you a decimal, which is, and v is just that decimal times c. A little bit of algebra, nothing much, right? All right, here we go, number 11. We got a neon sign on outside the cafe. Flashes on and off. It's measured by the head cook. How does the head cook's frame of reference compare to the signs? It would be the same, hopefully. And then we got a spaceship moving towards Earth at a speed of this. Okay? And we want to know how much time elapses between the flashes. This is where all our verbiage around time gets kind of muddled. So in the Earth frame of reference, it's 4.5 seconds. But now that's really a moving frame of reference, isn't it? Because the ship sees it moving. So is the ship going to see it take a longer or a shorter amount of time?
Longer.
Why longer? Going shorter.
Well, no, it's going faster.
It's going to see a shorter period of time between each flash. The ship. Because if you think about it, each flash is spreading out. And the ship is coming in and hitting them. It's not accelerating, but it's going to hit them at a higher rate than 4.5 seconds. Because it's moving in between them. So, yeah, that was actually one of the videos. I don't know if we watched in here. But, so we expect a shorter time between every flash as seen from the ship's frame of reference. So this is all good to put into our y here. Of course, is all right. The time between flashes will be less as measured by the ship. I think that's probably good enough for us. you could flush that out a little bit, right? Because you could say, time contracts and everything. And this is where, if you go to your equation sheet, we have our equation for time equals gamma T naught. Which one is bigger, T or T naught? T. Gamma is always greater than 1. Right? So, this is going to be this will be measured from the ship, and this will be measured from the Earth. I don't know why I'm having trepidation on this one. Feeling like we're messing up, but we'll see. If we mess up, we'll blame it on Adam. We'll shoot right down the middle. How about that? So, I've got 4.5 seconds and 0.83 C. What's nice is since V is 0.83 C, V over C is just 0.83. Right? Remember, keep things in terms of the speed of light. The less times you got to put in 2.79, blah, 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 the better. So, we're saying T is the Earth. For me, that's 4.5 seconds equals T naught, equals gamma, 1 over square root of 1 minus 0.83 squared times T naught. And I want to see if I get this one right. Now I'm having doubts. I got 2.51. Let's see. 2 sig figs. Yeah, nope. You know what? They don't actually mean towards Earth. They're not thinking about it as waves going out. The problem designer. They're thinking of the ship going by Earth, which means they're going to see time slow down.
It says in the equation, in a spaceship moving at.
I know, but I think the person who wrote the problem wasn't thinking about it as signals coming off of the Earth. In other words, they weren't thinking of these flashes as going out from the Earth. They were thinking of it as, they're going to measure that time is passing slower on the Earth than on the ship. So that it's, I may be just thinking too deep into the problem. Or the writer of it wasn't thinking deep enough. So really what they want is, see, what I was picturing was, here's your Earth, and these signals are moving out from the Earth, equally spaced, and your little ship comes in and hits them, and is of course going to hit them at a greater rate, right? I don't think that's what they were thinking. They were thinking ship goes by, therefore their time is moving slower on the Earth than on the ship. And so they want to see this as being the Earth time, and this as being the ship time. So we were thinking about the problem in two different ways. Not a great. I would have said, I would have rewritten the problem to have the ship flying by the Earth rather than towards the Earth, because then that would have been just it's moving along. So now we just rearrange this where we're looking for t. We still have the same here. And this is my point, my 4.5 seconds. And that should give me a longer time as measured from the spaceship. So let's see if what that does. Yeah, I get 8.1. Yay!
Keep doing that, and I'm getting the wrong answer.